This video is going to look at inverse function and relations. So we want to be able to know and apply the definition of inverse, graph the inverse of a function or a relation, determine if the graph of an inverse is a function using the horizontal line test, and find the inverse of a function algebraically. So first of all, the definition of inverse is the ordered pair AB is in the relation if and only if the ordered pair BA is in the inverse relation. A simpler way to think of this definition that I like to use is just use switch x and y. So if you can just think the definition of inverse is switch x and y. Anytime you hear the word inverse, think switch x and y. The inverse of a function is denoted with this function notation f negative 1. So the negative 1 looks like it's in the exponent position, and that's the notation that is typically used to note an inverse. So remember, if our definition of inverse is switch x and y, if I want to find the inverse of this function here, f of x, I'm going to just, for each point, switch the x's and the y's. So this is going to be negative 27, negative 3, negative 8, negative 2. The negative 1 doesn't change. The 0, 0 doesn't change. The 1, 1 doesn't change. 2, 8 becomes 8, 2, and 3, 27 becomes 27 and 3. Remember that a function and the inverse are operations that sort of undo each other. So let's for a second look at this. So if we look at f inverse of f of, let's say, 2. So we're doing a composition, but we're doing the composition with a function and its inverse. So remember, when we do this, we work inside out. So f of 2, so if we look here, f of 2 is 8. So this becomes f inverse of 8. So then if we go to the inverse function, where is 8? So 8 is right here. So if f inverse of 8 gives me 2. So what I want you to notice is that the number that we started with and the number that we ended up with are the same, because the function and the inverse of that function are going to undo each other. It doesn't even matter what order we're working in. If we do, let's say we do f of f inverse of this time, let's say we're going to go negative 27. So this is going to be f of, so f inverse of negative 27 is here. That's going to give us negative 3. And then f of negative 3 is here, and that's going to give us negative 27. So again, the number that we started with and the number that we ended with are the same number. Okay, so if we look at the graph of a function and its inverse, so let's graph this in the blue here. Plot some of these points here. So negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, 2, 8. The 3 and negative 3 points are not going to fit on our graph here. So if we connect these dots, hopefully you recognize that as your cubic function. Then I'm going to graph the inverse points in orange. So here we're going to graph negative 8, negative 2, negative 1, 0, 0, 1, 1, and then 8, 2. Again, the 27 and negative 27 are not going to fit on our graph. So again, if I connect these dots together, this is the inverse of that function. So remember, this is my inverse, and the blue function was just f. What I would like you to notice here is that if I graph this line y equals x, the blue function and the orange functions, which are inverse functions of each other, are reflections over this line y equals x. We like to say that the graph and its inverse are reflections of each other over the line y equals x. So another example here that we're going to look at, we're going to graph this function and its inverse below. So this is one of our basic functions, square root of x with a shift in it of plus 3 under my square root, which means I'm shifting 3 units to the left. So just kind of giving us some points to plot here with my t-chart. The first thing I want to think about here is that my domain here is going to be negative 3 to infinity, because remember, x plus 3 has to be greater than or equal to 0. So if I plot some points here, if I plug negative 3 in for x, I'm going to get 0. I can't go less than that, so I have to go bigger than that. So if we plug negative 2 in for x, I'm going to get the square root of 1, which is 1. If I plug 0 in, that's going to be irrational. If I plug 1 in, 1 plus 3 is 4. The square root of that is 2. The next number that I can take the square root of easily is going to be 9. So that's going to happen when I plug 6 in for x. So 6 plus 3 is 9. The square root of 9 is 3. So I have some points here that we can plot. So we've got negative 3, 0. We've got negative 2, 1. We've got 1, 2. And 6, 3. So that gives me my graph of my function there. And then hopefully we can see that the range of this function is 0 to infinity. So if we look at f inverse, remember the definition of inverse is switch x and y. So now I'm going to switch the x's and the y's here. The inverse function, this is going to be 0, negative 3, 1, negative 2, 2, 1, and 3, 6. So then plotting these points, we're going to get 0, negative 3, 1, negative 2, 2, 1, and 3, 6. So connecting these dots together, we have the inverse graph, and then hopefully what we can see here is that my domain now is 0 to infinity, and my range here is negative 3 to infinity. So my domain and range from my original function switched to become my range and domain respectively of my inverse function. So remember, the definition of inverse is switch x and y, so even the domain and range values are going to switch because they are the set of x and y values. Again, if you look at this graph, you can see that these two graphs are reflections of each other over that line y equals x. So when I start with a function, the inverse will sometimes be a function and it will sometimes not be a function. If it's not a function, then we typically have to put some restrictions on that domain so that we can actually get the function part of the inverse. A quick way to determine if the inverse is going to be a function is to do what's called the horizontal line test. We looked at this when we talked about one-to-one functions. So the inverse of a relation is a function if and only if each horizontal line intersects the graph and at most one point. So if we take a look here, this graph is going to fail the horizontal line test. So this graph fails the horizontal line test, which means the inverse is not a function. Moving the horizontal line over to here, again, we can see that this fails the horizontal line test and therefore the inverse is not a function. Over here on this one, we can see as we move this all the way down from top to bottom or bottom to top, this is passing the horizontal line test because this horizontal line is never intersecting the graph in any more than one point. So this one passes the horizontal line test and therefore the inverse is a function. Down here at the bottom, it's talking about if f is a one-to-one function, then with domain and range d and r respectively, then the inverse is f inverse and it has domain r and range d respectively. So just what we talked about on the previous slide, that the domain and range from the function switch to become the range and domain respectively of the inverse. Okay, so just a quick review. Remember that the vertical line test tells us whether something is a function or not. The horizontal line test is going to tell us if the inverse is a function, and if both the horizontal line test and the vertical line test are passed, then that means that the original function and the inverse function are one-to-one functions. So looking at these graphs down here, applying the horizontal and vertical line test, graphs 1 and graph 4 are functions because they're going to pass a vertical line test. Graphs 2 and 3 are going to fail a vertical line test, so they are not functions. Graphs 1 and 2 are going to pass the horizontal line test, so their inverses are functions. Graphs 3 and 4 are going to fail a horizontal line test, so their inverses are not functions. So the only graph that is a one-to-one function is graph 1 because it passes both the horizontal line test and the vertical line test. So we want to be able to find the inverse of a function algebraically. So our rules are simply this. First, we have to determine that the original function we have is a one-to-one function so that we know that we can actually get an inverse function. Then we're going to switch x and y, and then we're going to solve for y. And then that will give us our inverse function. We need to be careful and state any restrictions on the domain that may occur. So we'll take a look at how that works in just a second here. So we're going to find the inverse of this function, and we're going to state any restrictions on the domain and range. So first, just think about your original function. So the domain of f here is going to be 1 to infinity. So if we take a look at that graph, we got our domain from the equation, and then we can get the range from the graph. So my range is going to be -3 to infinity. Next, we want to just write this in y equals form, so I'm just going to replace the f of x with y. Replacing the f of x with y just gives us y equals square root x minus 1 and then -3. Remember, my next step is to switch the letters x and y, so we're literally going to switch the letters. So we're going to write x equals the square root of y minus 1 minus 3. And now we're going to solve to get y by itself. So the first thing I'm going to do is just add the 3 to both sides. Now we're going to square both sides. So we get x plus 3 quantity squared equals y minus 1, and then we're just going to add 1 to both sides, which is going to give us y equals x plus 3 quantity squared plus 1. Simplifying this a little bit, we're going to get y equals x squared plus 6x plus 9, still the plus 1. So my inverse function is x squared plus 6x plus 10. So taking a look at the graph with its inverse, we can see that the inverse is a parabola, but that is more than the inverse of the square root function that we started with. So remember, we have to impose our restrictions on this. So my range from my original function was -3 to infinity, so that needs to become my domain for my inverse function. So I'm going to come back to my y equals, and I'm going to impose a domain restriction on here. And we're going to do that by using the domain restrictions that we used when we did piecewise functions. So I've got the graph in there, and then I want to restrict that to be just where x is greater than or equal to -3. And then I can see the graph with its inverse. Then I can see the graph with its inverse, and I can see that there are reflections over that line, y equals x. So we restrict the domain of the inverse function to be -3 to infinity, and we get that from the range of the original function. And then the range of the inverse function is going to correspond to the domain from the regular function. So this was 1 to infinity. And we can see that from the graph is confirmed there as well. All right, so here's just another example with a rational function. So here I'm going to start with my domain here. So my domain of my original function is going to be all real numbers except what makes my denominator 0, which is -1. So -infinity to -1, and then -1 to infinity. So taking a look at that graph, we can confirm that my domain is all real numbers except -1. And by looking at the graph, we can see that my range is all real numbers except +1. Again, I'm going to start by rewriting this into the y equals notation. And then we're going to switch the letters x and y. So there were 2 x's in the original equation, so then it becomes 2 y's in the equation once we switch the letters. Now we just need to do the algebra to solve. The first thing I'm going to do is get rid of that denominator, so we have x times y plus 1 equals y. Here we have to distribute the x so that then we can combine those y terms together. So we're going to have xy plus x equals y. Again, getting the y terms together, we're going to have xy minus y equals -x. Now I'm going to factor out the y, so I'm going to take out the y, which is going to leave me with x minus 1 equals -x. And then finally, we'll divide both sides by the x minus 1, so we get y equals -x over x minus 1. So my inverse function is -x over x minus 1. Again, taking a look at the graph and the inverse. Here I can look, the domain of my inverse is going to be all real numbers except 1, and I can see that just from my rules here because my denominator cannot be 0. So my domain for my inverse is all real numbers except 1, which was my range from my original function. And then we can see that the range of the inverse function is all real numbers except -1, which again corresponds to the domain from my regular function. So here we didn't have to place any restrictions on the domains and ranges because the original function was a one-to-one function and the inverse is also a one-to-one function. Lastly, we want to be able to prove that two functions are inverse functions, and we do this with a composition rule. We use this rule here, that if two functions are inverses of each other, their composition f of g and g of x will result in just the value of x. So we have to show both of those. So we have to do the composition f of g and simplify it. We have to do the composition g of f and simplify it. We have to show that those are both equal to x, and then make the statement that because they're both equal to x, we know that those are inverse functions. So let's take a look at an example here. Here we have f of x is 4x minus 12 and g of x is 1/4 x plus 3. So remember, if we want to prove or verify, both of those words tell us that we have to do this procedure. We're going to start by doing f of g of x, which is going to give me f of 1/4 x plus 3, which remember means we're going to take this 1/4 x plus 3 and plug it into the f function. So the f function says take 4 times what's in the parenthesis minus 12. And currently what's in my parenthesis is 1/4 x plus 3. So if we just do a little bit of simplifying here, 4 times 1/4 x is going to give me x, 4 times 3 is going to give me plus 12, and then we still have a minus 12. The 12 and the negative 12 cancel out, and we're left with x. So my composition f of g of x equaled x. So that's the start, and then we need to do the composition in the reverse order. So we're going to do g of f of x. So we're going to have g of 4x minus 12. So we're going to take that 4x minus 12 and plug it into the g function. And remember, the g function says we're going to take 1/4 of what's in the parentheses plus 3. Currently, what's in the parentheses is 4x minus 12. Again, doing some simplifying, 1/4 times 4x is going to give me x, 1/4 times minus 12 is going to give me minus 3, and then we've got the plus 3, which cancel out, and we have x. So we get f of g of x equals x, which also equals g of f of x. Therefore, f and g of x are inverse functions. One more example, we have f of x is x squared plus 1, and g of x is the square root of x minus 1. So we start with f of g of x, which gives us f of the square root of x minus 1, which gives us square root of x minus 1 squared plus 1. The square and the square root would cancel each other out, and we will get x minus 1 plus 1, which will give me x. Doing the composition the other way, we get g of f of x, which gives us g of x squared plus 1, which is going to give us the square root of x squared plus 1 minus 1, which will give us the square root of x squared, which is x. So again, we get f of g of x is equal to x, which is equal to g of f of x. Therefore, f and g are inverse functions.